To understand inductive lighting, let's examine a setup using 2 wire coils. You'll need a 120 volts power source, 2 rolls of number 12 wire, a light bulb with a socket, and a screwdriver. Electrical tape is optional. Firstly, you will create the primary coil. Take 1 roll of wire and wind it into a coil, leaving about 6 inches of wire at each end. You can secure the coil with electrical tape if desired. Secondly, you will connect the primary coil to the power source. Connect one end of the primary coil to the neutral terminal of the 120 volts power source. Then connect the other end of the primary coil to the hot terminal of the 120 volts power source. Thirdly, you will create the secondary coil. Take the other roll of wire and wind it into a coil, making it slightly larger in diameter than the primary coil. Place the secondary coil on top of the primary coil, ensuring they are not touching. Fourthly, connect the light bulb to the secondary coil. Connect one end of the secondary coil to one terminal of the light bulb socket. Connect the other end of the secondary coil to the other terminal of the light bulb socket. When the power is turned on, current will flow through the primary coil, creating a magnetic field. This magnetic field created by the primary coil will induce an electric current in the secondary coil, which will then power the light bulb. If a screwdriver is inserted into the center of the coils, it will become temporarily magnetized due to the magnetic field created by the electric current in the coils. The principle behind this setup is electromagnetic induction. When alternating current flows through the primary coil, it generates a changing magnetic field around it. This changing magnetic field interacts with the secondary coil, inducing a voltage and causing current to flow through it. The light bulb, connected to the secondary coil, then lights up due to this induced current. This is the same principle used in transformers to step up or step down voltage. In this case, the primary coil and secondary coil act as a simple air core transformer. The efficiency of this inductive lighting setup depends on several factors, including the distance between the coils, the number of turns in each coil, and the frequency of the alternating current. The closer the coils and the more turns each has, the stronger the magnetic field linkage and the more efficient the energy transfer. The screwdriver becomes magnetized because the changing magnetic field created by the coils aligns the magnetic domains within the screwdriver's metal. When the magnetic domains are aligned, the screwdriver exhibits a temporary magnetic field. The strength of the magnetization depends on the strength of the magnetic field and the material of the screwdriver. Once the current is switched off, the magnetic domains tend to randomize, and the screwdriver loses its magnetization. In a practical transformer, the primary and secondary coils are wound around a common iron core to concentrate the magnetic field and improve efficiency. However, this simple setup demonstrates the basic principle of electromagnetic induction in a clear and visual way. The number 12 wire is commonly used in residential wiring for 20 amp circuits. Its size is sufficient to carry the current needed for this experiment without overheating, assuming the power levels are kept relatively low. Always exercise caution when working with electricity. Ensure that all connections are secure and that the power source is properly grounded. If you are not comfortable working with electricity, consult a qualified electrician. This demonstration is for educational purposes only and should be performed with appropriate safety precautions. Understanding the relationship between electricity and magnetism is crucial in many areas of electrical engineering and physics. Electromagnetic induction is used in countless applications, from generators that produce electricity to wireless charging devices. By understanding these basic principles, you can gain a deeper appreciation for the technology that surrounds us every day. The current induced in a secondary coil depends on the rate of change of the magnetic flux and the number of turns in the secondary coil. The greater the rate of change and the more turns, the higher the induced voltage and current. The induced voltage can be calculated using Faraday's law of induction, which states that the induced electromotive force, or volts, in any closed circuit is equal to the negative of the time rate of change of the magnetic flux through the circuit. In simpler terms, the faster the magnetic field changes, the higher the induced volts. The direction of the induced current is such that it opposes the change in magnetic flux that produced it. This is known as Lenz's law. Lenz's law ensures that energy is conserved in the electromagnetic induction process. The energy supplied to the primary coil is transferred to the secondary coil, and any attempt to increase the current in the secondary coil will be met with an opposing force. The frequency of the alternating current also plays a significant role in the efficiency of the inductive lighting setup. Higher frequencies generally result in greater energy transfer, but also increase the losses due to skin effect and other factors. The skin effect is the tendency of alternating current to flow primarily on the surface of a conductor, which effectively reduces the cross-sectional area of the conductor and increases its resistance. This effect becomes more pronounced at higher frequencies. The choice of wire gauge is also important. While number 12 wire is suitable for this demonstration, larger gauge wire may be needed for high power applications to minimize resistance and prevent overheating. The resistance of the wire can be calculated using the formula resistance equals resistivity times length divided by area. The resistivity of copper is approximately 1.68 times 10 to the negative 8th power ohms meters. The length is the total length of the wire in the coil, and the area is the cross-sectional area of the wire. The cross-sectional area of number 12 wire is approximately 3.31 times 10 to the negative 6th power square meters. By calculating the resistance of the wire, you can estimate the power losses due to heat. Power losses are calculated using the formula power equals current squared times resistance. These losses can reduce the efficiency of the inductive lighting setup and cause the wire to heat up. In a real-world transformer, the core material plays a crucial role in enhancing the magnetic field and improving efficiency. Common core materials include iron, ferrite, and amorphous metals. These materials have high permeability, which means they can easily concentrate magnetic fields. The core material reduces the reluctance of the magnetic circuit, which is analogous to resistance in an electrical circuit. By reducing the reluctance, more magnetic flux is able to flow through the core, resulting in a stronger magnetic field and greater energy transfer. The shape of the core is also important. Toroidal cores, which are shaped like donuts, are often used in transformers because they provide a closed magnetic path which minimizes leakage flux. Leakage flux is the portion of the magnetic field that does not link the primary and secondary coils. Minimizing leakage flux improves the efficiency of the transformer. The insulation between the primary and secondary coils is also critical for safety. The insulation prevents electrical breakdown and ensures that current flows only through the intended circuit. The insulation material must be able to withstand the voltage difference between the primary and secondary coils without failing. Common insulation materials include varnish, epoxy, and polymer films. The thickness of the insulation depends on the voltage rating of the transformer. In high voltage transformers, the insulation can be several millimeters thick. The cooling of the transformer is also important, especially in high-power applications. Transformers generate heat due to the resistance of the windings and the core losses. If the heat is not dissipated effectively, the transformer can overheat and fail. Common cooling methods include air cooling, oil cooling, and forced air cooling. Air-cooled transformers rely on natural convection to dissipate heat. Oil-cooled transformers use oil as a coolant, which has a higher thermal capacity than air. Forced air-cooled transformers use fans to circulate air over the transformer windings. The efficiency of a transformer is defined as the ratio of output power to input power. Transformer efficiencies can range from 95% to 99% depending on the size and design of the transformer. Larger transformers tend to be more efficient than smaller transformers. The efficiency of a transformer is affected by several factors, including the core material, the winding resistance, and the operating frequency. To summarize, the inductive lighting setup demonstrates the basic principles of electromagnetic induction. By creating a changing magnetic field with the primary coil, voltage and current are induced in the secondary coil, which can then be used to power a light bulb or other electrical device. The efficiency of this setup can be improved by using a core material, minimizing leakage flux, and optimizing the operating frequency. Remember to always exercise caution when working with electricity and consult a qualified electrician if you have any questions or concerns. Electromagnetic induction is a fundamental principle that underlies many of the technologies that we use every day. From generators to transformers to wireless charging devices, electromagnetic induction plays a vital role in our modern world. Now, to dive even deeper, let's explore some advanced concepts related to inductive lighting and electromagnetic induction. Firstly, consider the concept of mutual inductance. Mutual inductance is a measure of how effectively the magnetic field produced by one coil induces a voltage in another coil. It depends on the geometry of the coils, the number of turns in each coil, and the permeability of the medium between the coils. The higher the mutual inductance, the more efficiently energy can be transferred from one coil to another. Secondly, explore the concept of self-inductance. Self-inductance is a measure of how effectively a coil induces a voltage in itself when the current through it changes. It depends on the geometry of the coil and the permeability of the medium around the coil. A coil with high self-inductance will resist changes in current more strongly than a coil with low self-inductance. Thirdly, analyze the concept of impedance. Impedance is the total opposition to the flow of alternating current in a circuit. It includes both resistance and reactance. Reactance is the opposition to current flow due to inductance and capacitance. The impedance of a coil depends on its inductance and the frequency of the alternating current. Fourthly, consider resonant inductive coupling. Resonant inductive coupling is a technique that can be used to improve the efficiency of wireless power transfer. It involves tuning the primary and secondary coils to the same resonant frequency. At resonance, the impedance of the coils is minimized and energy can be transferred very efficiently. Fifthly, look at magnetic shielding. Magnetic shielding is used to prevent electromagnetic interference. It involves surrounding a device or circuit with a material that has high permeability. The shielding material diverts the magnetic field away from the device or circuit, reducing the amount of interference. Sixthly, think about eddy currents. Eddy currents are circulating currents that are induced in conductive materials by changing magnetic fields. They can cause energy losses and heating in transformers and other electrical devices. Eddy currents can be minimized by using laminated core materials, which consist of thin layers of conductive material separated by insulating layers. Seventhly, evaluate the use of finite element analysis software. Finite element analysis software can be used to simulate electromagnetic fields and optimize the design of transformers and other inductive devices. It allows engineers to visualize the magnetic field distribution and identify potential problems before building a prototype. Eighthly, keep in mind the safety considerations. Working with high voltages and currents can be dangerous. Always take appropriate safety precautions when performing experiments with electromagnetic induction. Ensure that all connections are secure and that the power source is properly grounded. Ninthly, study the history of electromagnetism. Understanding the history of electromagnetism can provide valuable insights into the development of modern electrical technology. Scientists such as Michael Faraday, James Clerk Maxwell, and Heinrich Hertz made fundamental contributions to our understanding of electromagnetism. Tenthly, explore the applications of electromagnetic induction. Electromagnetic induction is used in a wide range of applications, including wireless charging, metal detectors, electric motors, generators, and medical devices. By exploring these applications, you can gain a deeper appreciation for the versatility of electromagnetic induction. Finally, consider further research. The field of electromagnetism is constantly evolving. New materials, devices, and techniques are being developed all the time. By staying up to date with the latest research, you can expand your knowledge and contribute to the advancement of this important field. The principles of electromagnetic induction also apply to transformers used in power distribution systems. These transformers are used to step up or step down voltage levels to efficiently transmit electricity over long distances. Step-up transformers increase the voltage for transmission, reducing current and minimizing losses due to resistance. Step-down transformers decrease the voltage for distribution to homes and businesses. The design of these transformers is critical for ensuring the reliable and efficient delivery of electricity. Additionally, electromagnetic induction is used in induction heating systems. These systems use high-frequency alternating current to induce currents in the workpiece, causing it to heat up rapidly. Induction heating is used in a variety of applications, including heat treating, forging, and melting metals. It offers several advantages over traditional heating methods, including faster heating rates, more precise temperature control, and improved energy efficiency. Furthermore, electromagnetic induction is utilized in magnetic resonance imaging, or MRI, machines. These machines use strong magnetic fields and radio waves to create detailed images of the inside of the human body. The magnetic fields are generated by large electromagnets, and the radio waves are used to excite the nuclei of atoms in the body. The signals emitted by these nuclei are then used to create the images. MRI is a powerful diagnostic tool that can be used to detect a wide range of medical conditions. In summary, electromagnetic induction is a fundamental principle with numerous applications in various fields. From power distribution to medical imaging, it plays a crucial role in our modern world. Understanding the principles of electromagnetic induction is essential for anyone working in electrical engineering, physics, or related fields.